Hello, students. This is Mr. Pickett, and what I wanted to do is I wanted to kind of take you through some of our notes here. During our note packet, we've learned about alpha decay or alpha particles, beta decay or beta particles, and gamma emission. And if we remember with alpha decay, what's happening is we're having some sort of unstable atom that is going to be releasing something called an alpha particle. Right? And what is an alpha particle? Well, it's basically a helium atom. Now, some of this might be kind of challenging for you, but again, recall that when something breaks down, what it's trying to do is to go from unstable to stable. And what it's trying to do is it's trying to take its number of protons and neutrons and trying to get them to closer to a 1-to-1 ratio. So one of the things that it does is it's going to release 4 things at once, and we're going to call those 4 things together a helium atom, otherwise known as an alpha particle. And what those 4 things are 2 protons that are positive and 2 neutrons which are neutral. Right? A couple things about the alpha particle, right? It's got a mass of 4, it's got a +2 charge, and it has a lot of energy, but because it's kind of big, it doesn't get through things as much. Then we have another thing that can happen when something is unstable and it's trying to become stable, is it's going to end up releasing a beta particle. Now, if we remember, a beta particle is basically just an electron. And again, we're trying to take something that is unstable and turn it into something that's more stable. And a beta particle is exactly what I just described. It's just a negative electron. And I can't really, I don't know if I can superscript that. Ooh, that is not it. So it's just a negative electron. Now, where does that electron come from? Well, what we do is we transform a proton that's inside of this unstable nucleus. And not a proton, we transform a neutron that's in this unstable nucleus, and we kind of break it apart into a positive proton and this negative beta particle, otherwise known as an electron. This beta particle is ejected from the nucleus. And what has happened is I've taken the number of neutrons and I've decreased it by 1, and I've increased the number of protons inside of the nucleus. Gamma emission, it's not a particle because it's releasing energy. And so it's literally electromagnetic waves or photons, if you will. Again, what it does is it takes something that is unstable and makes it more stable. It does not change the mass of the atom at all, or the identity of the atom. All right, so as a review, we're going to come back up here and kind of look at this piece of nuclear chemistry, if we will. We're looking at an element that's called uranium, and we have 2 numbers that are next to it. We have to remember that the larger number represents the mass. And if we recall, I'll write this up here, that the mass, that's this 238, is equal to the number of protons, and then adding that number to the number of neutrons. And that's basic chemistry 101. Sometimes we see the mass number in different places, but it's the biggest number that's associated with this element right here. And so this other number, this 92, is called the atomic number. And what the atomic number represents is the number of protons. So as a review here, we know that this is uranium and that it has 92 protons. We know that. Now, how many neutrons does it have? Well, we'd have to do a little bit of math. We would take 238 minus 92. If we take 238 minus 100, I have 138, and I add 8 more to that. So 138 plus 8 is 146. Now, that's not totally necessary for us right now, but we need to know the number of protons, which I'm just going to write that down here. So the protons is equal to 92, and the neutrons is equal to 146, if I'm doing my math correctly. 238 minus 100 138. 138 plus 8 is 146. Yes. Okay. Now, what I'm going to do is I'm going to show you what happens when uranium goes through all three of these types of fissions. All right. So let's say this particular isotope of uranium is radioactive. And so it's unstable. It definitely does not have the same number of protons as it does neutrons. So let's imagine that what it does is it breaks down. Okay. So what would that look like and what would happen to it on each one of these situations? Well, I'm going to take this uranium and I'm going to have to draw it. Yep, that's good. And take this uranium, 238. And it has 92 protons always. And it's going to go through, we're going to start with alpha decay. This means that the uranium is going to break apart into at least two different things. So the uranium is going to break apart. And if I remember alpha decay, that means that two protons and two neutrons are going to be taken away from this uranium. So my number of protons that this thing has is now 90. And the mass has decreased by 4 because there's 4 things. So my new mass is going to be 234. Now this uranium is no longer uranium anymore because it does not have 92 protons. So what you need to do is take a look at your periodic table of elements, which is what I'm doing right now. And I'm taking a look at what atom has 90. That is thorium, TH. I don't expect you to know that off the top of your head. I expect you to look it up. So we have thorium, TH. Now, let's make sure that our math checks out. I started with 92 protons, and because it's going through alpha decay, which means that this uranium is releasing 2 protons and 2 neutrons, you're going to see the 92 protons turn to 90, and the mass of uranium is going to decrease by 4. Then I'm going to do plus, because there's going to be 2 things that are going to be released, and I'm going to write alpha, which I'm not doing a very good job of drawing that symbol. And the alpha particle is made up of 2 protons, and it has a mass of 4. What I just did here is I had you take a look at what happens when uranium undergoes alpha decay. One of the things that during alpha decay is we release an alpha particle. And then the uranium is going to change into something smaller, like thorium. And if we do our math correctly, these 2 bottom numbers added together should equal this. And these 2 masses added together should equal this. That is alpha decay. This one is not as complicated as some of the others. Now, the next one we're going to go to, which I'm just going to do right here, is beta decay. So we're going to take uranium. It has a mass of 238. And it always has 92 protons. This time, this uranium is going to experience a type of fission that's called beta decay. And what's going to happen is we're going to release a beta particle. So some of you maybe can see the concept here. And I can write an E, but I like writing the beta symbol, which looks like a B, something like that, with a tail at the bottom. The beta particle, if you guys remember, technically has no mass, right? It doesn't have a mass. And it is not made up of a proton, right? So there's no protons that exist with it, 0. and it does not have mass either, but it's going to have a big effect on these two. So you're going to see me change the zeros here, and that'll make sense in a little bit. So let's remember what happens during beta decay. Well, one of the neutrons is going to change into a proton. I'm going to say that again. One of these beginning neutrons is going to change into a proton. So what we should see is the number of neutrons is going to go down and the number of protons is going to go up. So we are going to go from 92 and change it to 93. Remember, one of the neutrons is going to change into a proton. So we're going to see an increase of protons, just one. But if I take a neutron away and I make a proton, my mass does not change. So we have the same mass, but we have a different element. So the element instead of uranium is neptunium, which is NP, capital N, and lowercase p. Now, sometimes what you're going to see is instead of this written as a 0, it's going to be written as a -1. Now, that's not because a beta particle is negative. It's because when a beta particle is emitted, we're actually going to decrease the number of protons by 1, but not affect the mass because we're just converting one of the neutrons into a proton. So we're just seeing a little bit of a transformation. Again, I have some kids that struggle with this, but that's what happens during beta decay. We have a neutron that changes into a proton. It does not affect the mass because we're just changing what one of these looks like. We're ejecting a beta particle, and we're going to make uranium get smaller. Even though the number of protons gets bigger, we actually slightly decrease the mass, just a little bit. We can't see it here, but we're ejecting something out. Okay, that is beta decay. Now, the last one is easy for many students to write and to draw. We have uranium. It has a mass of 238. And it has a number of protons, 92. When it undergoes gamma emission, okay, we're going to release a gamma particle. And gamma is written kind of like this weird looking Y. Ooh. Something like that. A wave does not have mass and it has no protons. So that's how we list it. And if we don't change the mass and we don't change the number of protons, well, then we're still left with uranium. Now, I have kids that go, well, what the heck is happening? Well, imagine you have something that's really excited. It's got a ton of energy, and then it just needs to yell. That yell is energy. We're doing something, and it's going to just lower the state of energy that this uranium atom had before. So we have gamma emission, we have beta decay, and we have alpha decay. I just wanted to go through that with you guys so that way you could see it.